Since the birth of the transistor, there has been a continuous evolution in electronic component technology and package style. The wires or leads that extend out of the component package have consistently increased in number and changed in size, shape, and orientation. Regardless of the style or size of the leads, the mounting and interconnecting of the components onto the printed circuit or printed wiring board has typically been performed by inserting the leads through the holes in the board and then applying solder to create the interconnection. The soldering operation can be performed manually with a hand soldering iron, or by passing the entire assembly over a wave of molten solder. During the 1970s, a different style of component began to emerge. Some of these components still had leads extending out from the package, but the leads were designed to be attached to the surface of the board rather than inserted through the mounting holes. Other versions of these new component styles had metallized terminations instead of leads, again intended for interconnection to the surface of the board. These surface-mounted components offered several advantages over through-hole components. First, since the leads or terminations didn't require mounting holes, the opposite side of the board was now freed up for other uses, such as additional conductors or components. The move away from through-hole components provided the potential for significant size and weight reduction, often as much as 50% for a typical multi-layer board. But even with surface-mounted components, there is still a need for some kind of hole to make the interconnections between individual layers of circuitry. A much smaller hole, called a via, is used to perform this function. There are three types of vias. The first is the through-hole via, which can be used to carry signals from one side of the board to the other, and to any of the layers in between. Via holes can also be located inside the board, completely between the inner layers. This type of interconnection is called a buried via. A buried via uses none of the outer surface area of the board in providing this electrical connection. Another type of via hole, called a blind via, begins on the outer surface of the board and extends down through one or more of the inner layers without exiting the other side. Since blind and buried vias are only located on specific layers as needed, there is considerable space savings on each of the remaining layers. All three types of vias can have a much smaller diameter than a typical mounting hole, since they don't have to accommodate a mounting lead. Smaller holes take up less room, which leaves even more space for additional conductors. Now you can see how surface mounting using vias instead of component mounting holes allows for a significant increase in circuit density within the same size area. There are other benefits of surface mounting that are less visible but equally important. For electronic circuits that are designed to operate at high signal speeds or high frequencies, the components can now be located closer together. The less distance the electronic signals have to travel from one component to the other, the faster the signals will arrive, with less overall degradation to the quality of the signal. This ability to move the signals between the components more quickly is a major development. Now circuit boards can be less of a limitation in the overall processing speed of the circuit, and even faster operating times can be achieved. But like everything else, there are trade-offs and challenges that must be overcome before surface mounting can replace conventional through-hole technology. One of the most significant differences is the configuration of the solder joints. Since surface-mounted components do not have the mechanical advantage of a mounting hole and a lead clinched to both sides of the board to secure the connection, there can be a major difference in the overall strength of the component attachment. Since surface-mounted solder joints have to provide both the mechanical and the electrical connection to the board, the strength or overall quality of the solder joint is even more critical than comparable through-hole connections. And as with through-hole joints, the acceptance criteria varies depending on the type of product that the components are being used in. For example, a pacemaker will obviously have more stringent reliability requirements than a home video game. And while it is desirable to have nothing but perfect solder joints for every lead or termination, we all know that there are a multitude of factors to control in the soldering process. For example, the environmental conditions of the soldering area, contamination of the solder or of the parts, any of which can result in a less than perfect solder joint. Most of these aesthetically imperfect solder joints will still function electrically and mechanically. The problem is that they may tend to fail earlier than a perfect joint when subjected to stress or strain. But this may not present a problem, depending on where the equipment will operate and also the overall life expectancy of the end product. Of course, every solder joint must be able to withstand the rigors of vibration during shipment and the stress of repeated temperature change, such as the thermal cycling resulting from turning the finished product on and off. Initially, each company defined their own acceptance criteria for these new surface mount solder joints based on the nature of their products. Obviously, there needed to be an industry standard to ensure consistent quality. However, standardization was more difficult because the styles of the surface mount component leads kept evolving in order to adapt to the demand of more leads in smaller package styles. In order to define acceptability requirements, various IPC committees developed criteria for 3 classes of solder joints. Class 1 requirements cover solder joints for use in consumer products such as radios and TVs. Class 2 covers commercial products like computers or business equipment. Class 3 requirements cover high reliability applications like aerospace or life support systems. In this series of videotapes, we will identify the common surface mount components and describe what a preferred solder joint should look like for each of the classification types. We'll look at some examples that could be acceptable depending on the application of the end product. We'll also look at solder joints that are definitely not acceptable no matter where they're being used. Then we'll discuss some of the causes of solder joint imperfections to aid you in understanding why a particular type of joint may vary in appearance. This information should help you to make the right acceptability decision for each specific kind of imperfection. We will also refer to the Joint Industry Standard or requirements for soldered electrical and electronic assemblies, developed by members of IPC and EIA. This specification is called ANSI J Standard 001 and incorporates information resulting from the latest reliability studies from around the world. Because requirements and specifications are constantly being updated to reflect the latest technology, IPC always welcomes your company's comments and recommendations on our standards by using the form provided in the back of each document. Whatever soldering specifications you use, they are likely to contain the same terminology to describe the attributes of a solder joint. Perhaps the most important term in the entire soldering vocabulary is the concept of wetting. Wetting is defined as the formation of a relatively uniform, smooth, unbroken film of solder, metallurgically bonded to a basis metal. Various degrees of wetting are characterized by the angle of contact between the solder and the base metal. A smaller contact angle between the two surfaces is a general indication of better wetting and a stronger bond. A larger contact angle indicates a decreased ability of the solder to wet and flow over the surface. On any type of solder joint, the preferred wetting angle is less than 90 degrees. A contact angle that exceeds 90 degrees usually indicates poor wetting or excessive solder. If a solder joint has a convex appearance as a result of excessive solder, however, it can be difficult to tell whether the surface is properly or poorly wetted. One attribute of a properly wetted joint is the presence of a smooth and uniform layer of solder, both on the surfaces of the lead or termination and on the surface of the land. The solder should also feather out smoothly onto the fillet or outline of the solder joint and be slightly concave or curved inward. One of the more easily detected conditions is non-wetting. Non-wetting is where the solder simply does not bond to the surface of either the land or the lead or the termination. Complete non-wetting is an unacceptable condition for any class of solder joint. De-wetting, by contrast, is characterized by irregularly shaped mounds of solder that are formed when the solder pulls back, almost as if it had changed its mind about wetting. De-wetting is harder to identify and may appear as a partially wetted condition, since the surfaces can be wetted at some locations while the base metal is covered with only a relatively thin film of solder in other places. Various degrees of de-wetting or non-wetting may be acceptable, depending on the nature of the final product. We will define the acceptance criteria for each type of component lead as we review them individually. The first style of component we will evaluate is the leadless chip component, which includes discrete resistors, capacitors, and inductors. Chip components come in various sizes and shapes. They can either be flat or cylindrical. In the resistor group, there are two main types: thin film and thick film. The resistive element is typically mounted face up to help dissipate heat away from the board while the component is in operation. Chip resistors aren't usually marked with the standard color code found on through-hole resistors, although a thick film chip resistor will usually have some form of colored resistive layer, with a protective coating on one side of the component and a white ceramic material on the other side. A chip capacitor, on the other hand, will typically be the same color on both sides, usually brown, although there is no existing universal standard for chip or resistor colors. There is also a height difference between chip resistors and capacitors. Usually the ceramic resistors are only about half as thick as ceramic capacitors. A chip inductor will usually have some type of encapsulated coil bonded onto a rectangular carrier. Many of these chip components are square or rectangular. Both ends will always have some type of metallized terminations on their exterior surfaces rather than leads. The design of the end metallizations comes in several different styles. For example, chip resistors might have 3 metallized surfaces or faces for soldering the components to the lands on the board. Chip capacitors may have 5 metallized surfaces that wrap around all of the corners of the component. Some chip components might only have terminations on the end and bottom surfaces. Generally speaking, the more surfaces the component has to solder onto, the stronger the solder joint should be. For example, if the solder joint can wrap around the edges of the chip component, it will have more surface area to bond onto. All of these passive chip components are quite small and difficult to mount onto the board by hand with any type of consistent results. Typically, these components are positioned or mounted onto the lands of the circuit board by an automatic placement machine. There is usually a solder paste which is screened, stenciled, or applied by the placement machine onto the lands prior to mounting the components. The solder paste will temporarily hold the chip components in place until the entire assembly is heated in some type of a controlled heat source. This type of soldering operation is called reflow soldering, since the solder paste is heated and then reflowed to form the solder connections. 3 current methods for reflowing solder include vapor phase reflow, where the entire assembly is subjected to a heated vapor that melts the solder and causes it to reflow; infrared or IR reflow, in which infrared lamps heat the assembly, causing the solder to reflow; and convection reflow, where circulating hot air reflows the solder and attaches the components. A combination of the last 2 methods, IR convective, uses both infrared energy and heated air in the same process, and is proving to be a popular and versatile approach. Still, there are other systems for mounting and soldering components. As an alternative to using solder paste, an auto placement machine can instead apply a precise amount of adhesive on the surface of the board. Or this adhesive may even be applied through a finely cut stencil using a squeegee. Either way, the placement equipment will then position each component directly on top of the adhesive to temporarily hold it in place until the soldering operation. After all of the components are positioned correctly, the adhesive is cured or hardened by heating the board in an oven or exposing it to ultraviolet radiation. Then the entire assembly is passed over a solder wave to form the solder connections between the component terminations and the lands on the printed wiring board. Depending on the method used, the texture and shape of the solder joints may vary slightly. Vapor phase reflow solder connections will have a tendency to be slightly duller than a wave solder joint. This discoloration is caused by a slower cooling rate and by contact with the chemicals used in the vapor phase process. This type of discoloration will generally not influence the strength of the connection. Wave solder joints tend to be fuller than the average reflowed connections, since there is more solder available in a solder wave than in a pre-applied solder paste. The orientation of the components as they pass over the solder wave can also affect the shape and size of the solder fillets. In some cases, the solder joints on the trailing edge of a component may be more concave than the fillet on the leading edge. This effect is referred to as shadowing. The location or orientation of a component on the board can also affect the shape of a solder joint. Again, slight variations in the amount of solder or the size of the fillet can be expected to occur. That's why it's important to be able to distinguish an acceptable solder joint from a rejectable one. Now that we've explained some of the key terms we'll be using throughout our discussion, let's take a look at a flat chip resistor as we begin to evaluate the specific requirements for this type of surface mount solder joint. The first condition that needs to be evaluated prior to discussion of any specific defects is the physical size of the solder joint. Unless there is a sufficient amount of solder to make the connection, the solder joint may be too weak to stand up to mechanical vibration from transportation or temperature cycling from the heating and cooling of a solder joint caused by turning the device on and off. The minimum dimensions for all types of surface mount solder joints are defined in the ANSI J standard 001. The requirements for different termination styles, such as 3-face, 5-face, or so on, and for critical dimensions of the solder joint, like the height of the fillet, the length of the overhangs, will vary from product class to product class. The best way to approach it is by first knowing which classification of product you are manufacturing. It's natural that some inspectors will want to make sure that their boards contain only the highest quality solder connections. We're all concerned with quality, and we all want our products to be the best they can be. But it's important to keep in mind that there will be variations in the solder joints. There will be some slight overhangs, and some components will have a little less solder than others. These are often just random process variations within the range of acceptable process control. Even though the acceptance criteria have been agreed upon by the electronics industry as a whole, if one inspector were to demand Class 3 or high performance requirements in a Class 1 product, that could create unnecessary rework. Rework should always be avoided if possible, not just for the sake of eliminating unjustified process steps, but to avoid the possibility of damaging an expensive assembly. Now that we understand why the minimum dimensions of a solder joint are specified, and why the adherence to the appropriate classification is essential, let's begin by explaining some of the dimensions that will be important throughout our discussion. We define the width of a component land or pad by the letter P. The width of the component termination will be specified by the letter W. As we mentioned before, these components can sometimes be positioned just slightly off-center, which will result in a side overhang condition. The specific amount of overhang will be called dimension A. Just how much can the termination hang over the component land? The specific allowances for rectangular or square-in components, for example, are defined in Table 9.5 of the ANSI J standard 001 for all three classes of products. For both Class 1 and Class 2 assemblies, the amount of side overhang is limited to 1/2 of the width of the termination, or 1/2 of the width of the land, whichever is smaller. There is also a maximum overhang limit of 1.5 millimeters that this overhang cannot exceed. If the overhang exceeds 1.5 millimeters, even though it doesn't extend halfway off of the land, the solder joint would not be considered acceptable. Class 3 requirements allow only a 25% overhang, again a maximum of 1/4 the width of the land or termination, whichever is smaller. There is also a maximum allowable side overhang limitation of 1.5 millimeters. To actually measure all of these dimensions for every solder joint is impractical in the real world of manufacturing. These criteria should be used to define the lower control limits of the component placement and soldering operations. Discuss with your trainer what to do whenever you see a misalignment that is close or slightly exceeds those acceptance requirements. Now let's review and make sure you understand everything we've discussed so far. We've learned that the strength of a surface mount solder joint is more critical than a through-hole solder joint, since a surface mount joint provides the mechanical as well as the electrical connection. We defined wetting as being a smooth, unbroken film of solder, which can be characterized by the contact angle of the solder. Less than 90 degrees is desirable, over 90 degrees is not. We defined the preferred shape of a solder fillet as being concave and smoothly feathered onto both of the metals. Then we looked at various samples of dewetting. We'll define the acceptance requirements for those conditions as we go through each of the different lead types during the rest of this series. We identified passive components with metallized faces or terminations on the end surfaces of the component. We discussed both reflow and wave soldering and explained that there are visual and size differences in the joints formed by the two methods of soldering. We explained how the position of the component on the board and the direction of travel over the solder wave can sometimes cause the leading edge of the component to exhibit a convex fillet and the trailing edge to have a concave shape. Then we discussed why it's important to apply only the correct class of requirements to your products. If you're ever in doubt, just ask your supervisor. It doesn't indicate that you're inexperienced, it shows that you care about the quality of your work. And finally, we went through the first example of reviewing the maximum overhang dimensions for a rectangular chip component, as shown in Table 9.5 of the Joint Industry Standard. If you have any questions on this first example, or on anything else we've covered in this introductory videotape, now's a good time to discuss them with your instructor before proceeding to Part 2, where we will go into more depth on specific requirements for rectangular chip components.